Hi guys, we are from Group 24. Today we were given a task to give a presentation on horizontal well testing. Before discuss about further details, allow me to introduce myself first. My name is Yap Ren-yi, the first speaker. There are 5 members in a group. First of all, in our lesson outcome today, we are focusing on describing the horizontal well testing model together with its characteristic flow regime. Secondly, to provide the equations for dimensionless variable, radial flow in the vertical plane, linear flow regime, and pseudo-radial flow. Next, to briefly describe the derivative behavior of horizontal well, and to provide equation for the calculation of two types of scheme. In order to fulfill the lesson outcome, we have prepared 5 lesson content, which are flow regime of horizontal well, dimensionless variables, equation for the characteristic regime, derivative behavior, and lastly skin of horizontal well. Before we going deeper, let us know about little bit about horizontal well testing. Advances in drilling and completion technology have placed horizontal well among the techniques used to improve production performance. Horizontal drilling is also efficient to increase the well surface area for fluid withdrawal, than in the result of improving the productivity. From this figure, the pressure behavior of horizontal well in homogeneous reservoir with ceiling upper and lower boundaries. As shown in this figure, the well is strictly horizontal. The penetration half length is L and depth W. Define the distance between the drain hole and bottom ceiling boundary. The vertical part of the well is not perforated. There is no flow towards the end of the well and the well conductivity is infinite. The KH here represents the horizontal permeability and KV represents the vertical permeability. Next, this is the flow characteristic of the flow regime. In an infinite system, the geometry of the flow line towards a horizontal well produces a sequence of 3 typical regimes. On the corresponding pressure and derivative response illustrated in this figure, 3 characteristic behavior are displayed after the well bore storage unit slope straight line. There are 3 types of flow regime, which are vertical radial flow, linear flow, and lastly horizontal radial flow. The first regime is radial flow in a vertical plane. On a log-log derivative plot, the well bore storage hump is followed by a first stabilization. During this radial flow regime, the permeability thickness product is vertical permeability times horizontal permeability square root it times 2L. This equation is defined with the average permeability in the vertical plane and the well effective length 2L. When the ceiling upper and lower limits are reached, a linear flow behavior is established. The derivative follows a half unit slope log-log straight line. Later, the flow line coverage from all reservoir directions towards the well, producing a horizontal radial flow regime. The derivative stabilization corresponds to the infinite acting radial flow in the reservoir. The permeability thickness product is horizontal permeability N times the thickness H. So I will pass it to my friends to discuss further.
Hi, my name is Yasser. Dimensionless variables for a horizontal well with well-bore storage and skin. The dimensionless variables are defined with respect to the total formation thickness in the previous equation. Gives the dimensionless pressure. In the case of permeability, entropy between vertical and horizontal direction and equivalent. Isotropic solution is used by introducing the anisotropy term vertical permeability over the horizontal permeability and the definition of the dimensionless vertical distance. When the vertical permeability is low, the apparent vertical distance are increased. The apparent open interval thickness HA and position of the horizontal drain hole with respect to the lower boundary of the zone Z are defined respectively, which HA equals to H square root of the horizontal permeability over the vertical permeability, and Z WA equals to ZW square root of horizontal permeability over the vertical permeability. The circular section of the horizontal well is changed into ellipse, and the horizontal well behaves like a cylinder with the apparent larger equivalent radius of the previous equation. With large entropy, vertical permeability over horizontal permeability RW can be 2 or 3 times larger than the actual bore radius, and the resulting entropy scan clearly negative. Similar scan coefficients are defined for horizontal well, the mechanical infinitesimal. Several scan, the entropy scan, the apparent scan during the vertical radial flow regime, the geometrical scan, and the total scan during the horizontal radial flow. The definition of all scan are presented in detail in the subsequent sections, and the definition of the dimensionless terms. Several well parameters can be used for the reference length, considering the well bore radius, or by analogy with wells interpreting a fracture of half length with the well half length. For the dimensionless time, for example, Td can be expressed by Tdl equals to 0.0026 for permeability over porosity, viscosity, total compressibility, length squared times delta T. No group of independent variables has been identified to provide an universal description of horizontal well responses as it has been possible with most of models. Many authors use the ratio Hd of the apparent thickness Ha of the previous equation by the well half length as the leading parameter of horizontal well behavior. And for this, Hd equals to Ha over L equals to H over L, the square root of horizontal permeability over vertical permeability.
Hello, my name is Zulhelmi Daniel bin Razali, so I will continue this video presentation. In the following section, the different limiting forms of the Kuchuk solution are presented, and the different skin coefficients defined from the horizontal well responses as described. For the radial flow in the vertical plane, during the vertical radial flow regime, the equation of the semi-log straight line is expressed from Kuchuk in the 1995 as in the slide here. Delta P is equal to 162.6 qdmu over 2 square root of k v khl and times log square root of kv times kh times delta T over porosity, viscosity, total compressibility, and radius of the Bosco minus 3.23 plus 0.87 SW minus 2 log half times 4 square root of kV over kh plus 4 square root of kh over kV. The second logarithm correspond to the negative anisotropy of S resulting from the equivalent well-bore radius, which is RWE. The total skin factor, which is SPV, measured from the early time radial flow analysis, combined with the well-bore mechanical skin factor SW and SNE, which is negative skin anisotropy. Here we can see these are the equations for total skin factor STV. Is equal to SW plus SNE equal to SW minus long square root of 4 times square root kV over kh times 4 times square root kh over kV over 2. For the linear flow regime, during the linear flow regime, the pressure changes as the square root of the elapsed time as the equation here on the slide. As you can see here, the pressure changes as the square root of the elapsed time. The first term of the equation is similar to the previous equation for a well intercepting a fully penetrating vertical fracture. With a horizontal well, the flow lines have to converge toward the well located at ZW in the formation thickness. This partial penetration effect produces a pressure drop expressed with the skin Fz. During the linear flow regime, the two skin effects Sw and Fz are additive. As you can see here, these are the formula for Fz, which is here Fz equal to negative 1.151 times square root of H over Kv H over L times log big bracket pi times radius of well over H times 1 plus Kv over Kh square root times sine phi Zw over H for the pseudo-radial flow from the reservoir. Using the well half length L as the reference for the semi-log analysis of the horizontal radial flow, the Kuchuk define delta P here uh, is equal to 162.6 times Q B mu over KH times H times log minus KH delta T over positive mu total compressibility times total compressibility times radius of the well bore square minus 3.23 plus 0.87 STH, where the formula of STH here, which is a total skin factor combined with the well bore mechanical skin factor SW and the geometrical skin SG. By comparing those two equations, we can get here STH, which is a total skin factor, is equal to here. And for the horizontal geometry skin, Sg is expressed also here on the slide. Sg is equal to 0.81 minus 1 L over radius of the well bore plus Xzt is equal to here 0.81 minus 1.151, and then we just substitute the value here. From the equation, the term 0.81 minus 1.51 minus I'm sorry 0.81 minus ln L over Rw is very close to the pseudo skin of a fractured well, and Szt describes the pressure drop due to the convergence of the flow lines before reaching the well. This term disappears when Hd is very small. For example, in the case of a long well and high vertical permeability Kv. That's all from me. Thank you.
Hello everyone, my name is Abdul Kudus. Today I am going to describe the derivative behavior of horizontal well. Due to the complex behavior of pressure and derivative responses, no type curves are available for horizontal wells. The derivative log-log curve is used for the identifications of the characteristic flow regimes, but the analysis is made by generating pressure and derivative responses with a computer or, when applicable, by using specialized plot straight lines. In example of a horizontal well response of previous figure, the last derivative stabilizations corresponds to pseudo-radial flow in the producing zone, whereas the first stabilizations describes the initial radial flow in the vertical plane. The average permeability in the vertical plane is defined as the geometric mean of Kv and Kh, and the permeability thickness product is 2 times the square root of Kv, Kh, and L. In dimensionless term, the level of the first stabilization is expressed with the dimensionless apparent thickness Hd, as shown in this equation. When both the upper and lower boundary have been reached, there is no vertical contributions to the flow anymore, and expansion of the drainage volume becomes strictly horizontal. If the length of the well is significantly larger than the reservoir thickness, most of the production is due to linear flow in front of the horizontal drain, and the flow contribution from the two ends of the well are negligible. During this intermediate time linear flow regime, the derivative follows a half-unit slope straight line. Once the linear flow regime has started, horizontal wells behave like wells intercepting an infinite conductivity vertical fracture of half length xf equals to L. The presence of an initial vertical radial flow regime before linear flow is simply seen as skin on the equivalent fracture model. As far the influence of L and kV over kh. With the TD over CD timescale, the location of the half unit slope straight line indicates the effective well half length L. When L is doubled, the line is displaced by a factor of 4 along the time scale, and as the first derivative stabilization is an inverse function of L, delta P of the first stabilization is twice as low. In examples of this figure and this figure, three well lengths are considered, but the permeability anisotropy kV over kh is adjusted in order to keep the same derivative stabilizations during the vertical radial flow regime. With this figure, the vertical permeability kV is relatively high and delta P for the first stabilizations equals to 0.223 is below the radial flow 0.5 line. In such cases, the horizontal drain produces a negative geometrical skin. Conversely, when kV is low, the first derivative stabilization is above 0.5, and horizontal well behavior tends to be equivalent to a well in partial penetrations. In the case of low vertical permeability, short horizontal well exhibit a positive geometrical skin and therefore an overall damaged well behavior. This is an important point and demonstrates that not all horizontal wells will increase productivity. And now I am going to talk about influence of Zn over h. First vertical radial flow lasts until one of the upper or the lower boundary is reached. If the horizontal well is not centered in the zone thickness, a hemi-radial flow regime can develop when only the closest limit is seen, as long as the second ceiling boundary is not reached. The shape of derivative curve is similar to that of a vertical well near a ceiling fault. The second derivative stabilization is at a level twice the first as illustrated in this figure.
Hi everyone, my name is Wang Weifeng and I'm going to describe the skins of horizontal wells. Since several distinct flow regimes are observed during horizontal well responses, several skin parameters can be defined to describe the different flow geometries even though the infinitesimal skin damage SW is constant at the wellbore. Furthermore, since the skin factors are a dimensional pressure drop, several references can be used to normalize the different change in pressure skin. In the following, I will summarize the influence of the well and reservoir parameters on the two skins usually estimated from analysis. The first type of skin is mechanical skin, SW. As an extension of the total horizontal radial flow skin concept SPH used in the previous equation, the infinitesimal wellbore skin SW is sometimes also defined with reference to a vertical well of radius RW and permeability KH, horizontal permeability. The resulting skin parameter SW prime does not define the completion quality as does SW of previous equations. SW prime is equal to 0.5 times dimensional height times the normal skin vector and is also equal to h over 2L times square root of horizontal permeability over vertical permeability times the normal skin. And as for the second type of skin is geometrical skin. Several hypotheses of permeability and isotropy where vertical permeability over horizontal permeability are considered, assuming a constant formation thickness h over Rw. When the vertical permeability is very large and is considered infinite, the partial penetration term SZT cancels out and the negative geometrical skin Sg is a linear function of log L
over RW. When a vertical pressure drop is introduced as on the examples Kv over Kh less than 1, the geometrical skin is less negative and the curves reach the infinite vertical permeability behavior only when the drain hole is very long. As of now, we have already described the models used in horizontal well, followed by the characteristic flow regimes of horizontal well, and then we also talk about the dimensional variables used in horizontal wells testing, followed by the equations which we use to describe the characteristic regimes. And then furthermore, we also study the derivative behavior of the horizontal well, and then lastly we talk about the skins of horizontal wells and how to compute them. Lastly, over the last decade, significant progress has been made in developing forward analytical models and interpretation techniques for horizontal wells. The effects of the top and the bottom boundaries, such as no flow and constant pressure boundaries on the transient behavior of horizontal wells, have been recognized. Flow regimes have been presented for system identification and for estimation of a number of reservoir parameters. The pressure derivative is shown to be an effective system identification tool that can also provide initial approximations of the nonlinear estimation. Relying solely on nonlinear estimation without diagnostics may lead to an erroneous model and estimates. The behavior of a multi-layer reservoir with a horizontal well cannot be treated as an equivalent single-layer system with average properties. That's all from our group, and this is the reference that we use for this presentation. Thank you for your kind attention for listening to our presentation, and have a good day.